Good evening and welcome to the second event in our 2022 speaker series, Surprising Science, Borrowed Ideas Leading to Unimagined Consequences. I would like to acknowledge and pay respect to the traditional owners of the land on which I am this evening, the Ngunnawal people. It is upon their ancestral lands that the Australian Academy of Science is built. As we share our knowledge, teaching, learning, and research practices, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of this country. I'm Nanda Dasgupta. I'm a fellow of this academy, and I have the pleasure of convening this series together with Professor Drew Evans from the University of South Australia. Hello, Drew. And I'll hand over to Drew to take it over from here. Hi.
Thank you, Nanda. I'm really enjoying working on this series with you, with so many creative ideas we have coming throughout 2022. I'm joining you all today from Ghana country, and I too pay my respects to elders past and present. Thank you all for joining us for our second event in this fantastic series. Tonight, we will hear about prawns and pipelines. Dr Ha Truong and Dr James Gong will no doubt surprise you with their science and the connection between these two topics. Before we hear from them tonight, just a few things. If you'd like to join the conversation on Twitter, do so by using the hashtag #SurprisingScience. For those of us online in the audience, you'll be able to submit your questions by scanning the QR code on the screen. And for those live in the Shine Dome this evening, you'll be able to ask questions at the microphone during the Q&A session. So now, let's hear from our first speaker, Dr Ha Truong. Ha is an aquaculture nutritionist with CSIRO, with expertise in diet and ingredient evaluation, nutrient utilisation, and digestive physiology of prawns. She joins us now from Bribie Island. Please welcome Ha.
Thanks, Drew, and thanks to everyone for this opportunity. So hello from Gubbi Gubbi country, Bribie Island. As you can guess, this is a presentation about prawns. With Easter coming up, I bet prawns are on the essential list for many shopping trolleys. And it really is a worthy Australian icon, and I'll be giving some reasons why in this presentation. So Australians love prawns and consume about 2 kilograms of prawns per person per year. And about 40% of this consumption is during the festive season, so Easter and Christmas. But what many may not appreciate is where these prawns come from and the journey they've taken to get to our dinner tables. So there are two main ways where prawns are produced. The first being that they can be captured from the wild in the oceans, and this is referred to as capture fisheries. And the second is that they can be farmed in ponds on land, and this is referred to as aquaculture. So globally, crustacean production is on the increase, and this is mostly coming from an increase in aquaculture production. As you can see from the purple capture fisheries line, this production amount is beginning to plateau. And this is because the wild stocks are a finite amount, and this amount cannot be increased. And so in order to meet the increasing demand of wanting to eat prawns due to the increase in global populations, then aquaculture is really the only way that these demands can be met. And here shows some of the main prawns that are aquacultured, and there are many more. just like in cattle production, where there are many different breeds depending on what location you're from, there are also many different species of prawns depending on the part of the world that you're in. And so in Australia, we produce two species of prawns, the banana prawn and the black tiger prawn. And these two prawns are endemic to Australia. So I can already sense the main question on top of everyone's mind is, what is the difference between a prawn and a shrimp? Well, unfortunately, the prawn or shrimp has an identity crisis, and we won't be able to solve it today. But if you want to get technical, prawns are defined by their middle segment, which overlaps the head and the tail, and so allows them to bend more easily than a prawn, where each body segment is overlapping the following segment. But these nuances are lost when we talk about prawns and shrimp casually. And this would be a prawn if you're using the Queen's English, or a shrimp if you're American. And so let's use these two examples of our main prawn species that are being produced. So you have the white-legged shrimp, which is mainly produced in America, and we have the black tiger prawn, which is produced here. And so if you can look closely, you could see that each segment is overlapping the one following it. And so really they should both be called prawns. But the white-legged shrimp has been around for a really long time in terms of farming, and it's one of the original prawns that have been farmed. And so the name has stuck, the white-legged shrimp, and it's unlikely to be changed. And due to its reputation, it's allowed to be called a shrimp. And you can see how advanced this white-legged shrimp industry is when you compare the amount of production globally, where the white-legged prawn is far more advanced in the speed it has increased in production compared to the black tiger prawn, which is a really immature industry with a much slower rate of growth. In Australia, Queensland is the main location where black tiger prawns are being produced, and we produce around 6,000 tonnes a year, which really only equates to 0.1% of the global production. But it is forecasted that in the next coming years that this production will greatly increase. And this is a huge opportunity for Australia to be catapulted into one of the main producers of black tiger prawns in the world. This potential is exciting and is mostly coming from the increasing investment going into Northern Australia, where it is perfectly suited for the culture of black tiger prawns. But when we talk about increasing a farming industry, we also have to think about how we can do this sustainably. And to think about sustainability, we have to think about the inputs and outputs coming into this system, and how we can minimize the waste and better utilize waste to be used as inputs. And so this term is used to be described as a circular bioeconomy. One of the main areas that has already been very well researched in aquaculture is around the feed and making it more sustainable. And this is because feed also equates to the major cost of producing prawns. Major strides have already been made in this space, including the ones from CSIRO, where we have worked to develop a feed ingredient from sustainable sources that can be used to replace fish meal in aquaculture diets. And by adding this ingredient to diets, it can also promote healthier and faster growing prawns. But now we are shifting our focus to other areas of this production cycle. And so one area of interest is this sludge coming from aquaculture ponds. This sludge is highly nutritious in nitrogen and phosphorus, and so can be used to rear supplementary cultures, secondary culture items, such as these worms. Also, specifically, these worms are marine polychaetes or mangrove worms, And they're a highly prized and valuable live feed that is required to mature broodstock prawns, and broodstock prawns being the mummies and daddies of the prawn world. And so here we have a picture of these very big prawns. These are our broodstocks. They're about 150 grams, but they can get as big as 200 grams in a very short lifespan of 2 years. And so we never grow these prawns this size for the market, but we do need these size prawns to create the next generation. And here they are, the next generation of prawns. So one female can create 1 million little babies, and she does this by fertilizing her eggs from sperm that she's collected from the male after it has molted. And then these eggs will develop into larvae, which go through several complex larval stages before they become a prawn that we can recognize that we see in the supermarket. These little larvae are reared in what we call nursery tanks and then are fed off cultured algae. And then they have a long journey, about 6 months before they reach what we see in the supermarket. So the next potential area for utilizing waste is in our households. We generate a lot of waste that is organic and highly nutritious, and unfortunately, most of it is ending up in landfill, but this can be captured and fed back into the food production system by utilizing it as an ingredient for prawn feed. So we're collaborating with Food Recycle, who have patented technologies in transforming food waste into a food-safe ingredient that can be used for animal feeds. So in particular, we're looking at 5 different streams. We have fish offal, which comes from the fish market. We have restaurant and pub waste. We have abattoir waste, bakery waste, and vegetable and fruit waste from fresh food markets. And so the composition of all of these different food streams is very different. And so to know whether they are suitable to be used in a prawn diet, we have to do some digestibility studies to understand how well they are digested and utilized by the prawn. So when we do this in a digestibility study, here are our results for protein. And we can see that the fish offal, the pub restaurant, meat and bone meal, and bakery waste can be digested by the prawn, and they are releasing nutrients for the prawn to use. Whereas for the vegetable and fruit waste, it is very poorly digested and even has a negative effect on protein digestibility. And so we know from this study that fruit and vegetable food waste is not suitable for prawns, whereas the other streams are. This isn't very surprising because prawns are highly carnivorous species and require up to 50% of their food to be protein. And this requirement has to be met throughout their life cycle because prawns are also highly cannibalistic. And if given the chance, they will certainly eat each other. So in order to avoid that, we have to supply them with nutritious diets that they can eat instead of each other. And so in order for prawns to grow, after being fed a very nutritious diet, they molt. And so before they molt, they absorb a lot of water into their blood to expand the inner shell. And then this gives them space to put on muscle protein. And once they do molt, then they consume their molt. So nothing is lost. They retain all of their nutrients throughout this process. And so another area of opportunity to utilize waste is in industry. And this is when after the prawn has already been cooked and eaten by the consumer. In Australia, particularly, we do not eat the heads of prawns. So only 50% of the prawn is actually consumed and the rest ends up in landfill. So there is an opportunity here for, at the processing stage, to capture these heads and then convert them into a form that can be utilized in other industries. For example, we can hydrolyze these heads into an ingredient that can be fed back into aquaculture for different species, and utilize this waste rather than it going into waste. And then the other area we can look into is the use of the shells, where the prawn shells is really rich in chitin and glucosamines, which are a bioactive compound that are commonly used for nutraceuticals and pharmaceuticals. And prawns provide a natural source of these compounds. So we're looking at more of the therapeutic potentials of prawns and how we can optimize this extraction process to better grab these bioactives from these waste products. And so using all of these strategies together, we are able to create a much more circular economy for prawn production. And really it's taking a very linear pipeline of prawn production and turning it into a circular pipeline. And so I hope this allows you to enjoy your prawns better during this Christmas. Thank you, that's me.
Thank you, Ha. It's absolutely amazing to hear so much about prawns and to be honest, a lot that I didn't know. So there's a lot more when I look down at my plate over Easter and especially at Christmas and look at the prawn to understand how much of, I guess, the circular economy is going into it. And to be honest, a significant amount of research and development that goes in behind just the pathway that those prawns take to get to us, and then what we can do to utilize waste for their production, but also the waste from their production to feed back into a lot of other areas of society. So absolutely fantastic, Ha. Thank you. And now I'd like to introduce tonight's second speaker, Dr. James Gong. So James is passionate about solving pressing issues in the water industry. His key research interests and expertise include smart water monitoring, smart water network, design and data analytics, leak and burst management in water distribution systems, and condition assessment of civil infrastructure. To be surprised by how his work is connected to prawns, please welcome James.
Kilometers of water pipes in the urban water sector alone. And that's enough length to wrap around the Earth for more than 5 times. On those pipes, we have about 36,000 pipe breaks every year, and we lose about 255 gigaliters of water. That's enough treated water to supply an additional 1.5 million homes, or 3.7 million people. So, to address the big challenge of aging water assets, my team at Deakin University and my collaborators at the University of Adelaide have been working on cost-effective pipeline condition assessment technologies. So here, this little animation illustrates the principles of the pressure wave-based pipeline condition assessment technology we developed. Firstly, we introduce a side discharge out of the pipeline. Then, we shut it off very quickly. So it's quite similar to shut your tap at home. The sudden stop of the flow will generate a pressure rise. And this pressure perturbation will propagate along the pipe in the form of pressure waves. So this is also known as water hammer waves. If there are significant physical discontinuities, such as leaks or pipe sections with extended corrosion, reflections will occur, and we can capture those reflections by pressure transducers. So this is what you would expect as the pressure response of a pipeline system. We have the original pressure, and then we have the introduced pressure wave. Then we have reflections from those anomalies. So by analyzing the pressure response of a pipeline system, we can tell whether there are problems, what are the problems, and where are the problems. So it's quite similar to the use of sonar waves to detect objects underwater. Well, as you can say, the introduced pressure wave is a key element in this technology. And we don't really want to introduce too big waves, right? Too much pressure can be harmful to the pipe system. So we want to control the size. So in that sense, the sharpness of the wave becomes very critical. It impacts the identifiability and also the spatial resolution. So here is an example to demonstrate this. So if we have a sharp pressure wave like this, so here is a pulse wave, and we have a section with some deterioration. So let's say it's an extended blockage or extended corrosion. Then when we have this sharp pressure wave, we will have sharp reflections, right, from the two boundaries of this deteriorated section. And here, this is what we would expect as the overall response. We can see the two reflections clearly because, they are sharp reflections. In contrast, if we have a mild pressure wave to start with, we will still have two reflections from the two boundaries. But reflections will be mild as well, and some parts of it will be overlapped. So the overall reflection becomes quite complex, and it's much more difficult to identify considering the background noise in real systems. So over the years, we have been working on different types of wave generators. So this is the wave generator we use for field projects right now. It simply follows the principle I described, establishing a flow and then shut it off very quickly. That results in a step pressure wave like this. The rise time is about 10 milliseconds, and the magnitude is about 5 to 10 meters. In hydraulics, we sometimes use meters to represent pressure. So 10 meters is equivalent to the hydrostatic pressure 10 meters underwater. Well, it looks quite fast, right? 10 milliseconds. However, if we consider other constraints like signal dissipation and dispersion, the very fast wave speed in the pipeline, the spatial resolution we can achieve on the current technology is about 10 to 20 meters. While that is already a breakthrough because we are able to do condition screening of very long pipelines, like kilometers of pipelines using this technology, but the spatial resolution is not high enough to pinpoint the problems for excavation. So, as mentioned, we've been trying to improve this technology for years, and we developed all sorts of fancy wave generators. Until one day, we came across this little creature, the snapping shrimp, also known as the pistol shrimp. Well, I'm not trying to argue about the name. I think the name probably comes from America. It could be, snapping prawn. But that's not the key point. The key point is this little creature, similar size to the banana prawns or the tiger prawns we just saw in the previous presentation. This little creature has some superpowers. And the secret lies in its large claw. Some researchers has published a paper in Science a few years ago to describe the secrets. Here is a simplified explanation. So when the large claw opens, the chamber inside is filled up with water. Then the claw snaps shut within 1 millisecond. That fast action will produce a high velocity water jet as high as 100 kilometers per hour. And this high velocity will decrease the surrounding pressure all the way to vacuum or the vapor pressure. As a result, we will have cavitation bubbles. And because everything is still underwater and under pressure, the cavitation bubble will collapse in no time, and the collapsing of the bubble creates powerful shock waves. As measured by those researchers, the shock wave generated was extremely sharp and powerful, as high as 80 kPa or 8 meters of pressure, even at 4 centimeters away. So, are you thinking what I'm thinking? Right? This is a clever idea, right? So we went to the Great Barrier Reef, and we caught a few beautiful snapping shrimps. And we put one of them into a laboratory pipeline. And, well, as expected, the shrimp lived happily there because, it's so used to pressure. Then we asked the shrimp to use its superpower, creating an extremely sharp pressure wave. And thanks to this sharpness, we were able to see everything in our experimental system, including the joints connecting pipe sections. That sounds wonderful, right? That's my 1-minute science fiction. Well, the true story is that, inspired by this shrimp, we developed a spark wave generator. So here, this magic box lifts the voltage all the way up to 2500 or more. When we press a button, this high voltage is applied to a spark plug, this one. And the spark plug simply does its job, just like in your car's engine. The electric spark underwater can create cavitation bubbles, and the collapse of the bubble creates the pressure wave we want. So, part of my science fiction has come true. So this is a laboratory pipeline system, a 25 millimeter diameter copper pipeline. So as mentioned, it was prepared for the shrimp, but instead we installed the spark plug onto the system. So here under this white cover. Well, on the top, you can see another device. That's another wave generator, but that's a story for next time. So here is a schematic to provide more technical details. This pressurized tank provided the water and the pressure we need for the whole system. The other end of the pipe was fully closed. Then the spark generator and the pressure transducer PT1 were installed just next to this closed end. In this pipe system, we had 2 sections with thinner wall thicknesses. The type B section and this type C section. So here you can see the wall thicknesses. These 2 sections were used to simulate sections with extended corrosion. So they like precursors of leakages. Right? If we can find corroded sections and fix them, we would prevent leakages and pipe bursts. Here we had another pressure transducer PT2 in between the 2 sections. So the purpose is to find the type B and type C section. Here are the results. The blue line was measured by transducer PT1, and the red line was measured by transducer PT2. Well, because the transducer PT1 was so close to the generator, so there were lots of interference. So we had to check the signal from PT2 for confidence. Here, this is a zoom-in look of the wave we generated. So we can see the wave was quite powerful. So it's more than 2 bars. So that's another unit we use. So 2 bars means 200 kPa or 20 meters. So that's fairly powerful. Also, the wave was extremely sharp. So here, if you check the duration of this main pulse wave we generated, that was less than 0.2 milliseconds. Now, let's have a look at the reflections. So thanks to this sharpness, we were able to see the reflections from the type B and type C sections clearly. For the type C section, the wave came from the end, traveled to the type C section, reflected by the 2 boundaries, then captured by transducer PT2. For the type B section, similarly, the original wave came from the end, reflected by the 2 boundaries, traveled back to the closed end, reflected again, finally captured by transducer PT2. So that's why we've got these 4 reflections overall. So the results are quite promising. However, we haven't been able to find a water utility brave enough to test this high voltage device. Well, that's not the end of the story yet. As mentioned before, leakage is a big issue in water distribution systems. In recent years, we have developed some new technology using controlled leaks to generate the pressure excitation we need. So here I will show you how we use leaks to find leaks. We reconfigured the system for the new experiments. We connected the water main to the laboratory system to provide the background pressure oscillations as you would expect in real systems. Here, L1 and L2 were 2 small leaks to be detected. G1 and G2 were 2 side discharge valves we used to produce continuous pressure oscillation. The mechanism is pretty much the same as leaks. So here is a photo of G2. Basically, it's a side discharge valve. Then we just open this, or partially open this, to create turbulence. And the turbulence will create pressure oscillations. P1 and P2 were 2 pressure transducers installed close to each other. J1 to J7 were pipe joints. In the time domain, the measured pressure simply looked like noise. The relatively large perturbations, with relatively low frequency or relatively long period, they were the background noise from the water main, from the real water distribution system. When we zoom in to the details, we can see lots of small amplitude, but very sharp pressure oscillations. These signals came from the leak and also from the side discharge valve we used for excitation. Then we developed some techniques to analyze the noisy signals from the 2 pressure transducers. And we derived a signal called paired IRF, or paired impulse response function. So one benefit of this signal is that responses from an anomaly come in pairs, and that helps to enhance the detectability, helps us to tell the real response from background noise. Here we can see the response from leak L1 is clearly shown as these 2 distinctive signals. To our surprise, we could also see the response from the two junctions, the J1 and the J2. And they were only 5 centimeters long each. So by now, my science fiction actually has come true. We have achieved very high spatial resolution, inspired by a shrimp, realized by a leak. So we are now working towards translating this research from the lab to the field. So all the results I presented were contributed by a large team of researchers and technicians. Most of the work was done in the hydretics lab at the University of Adelaide. Also, thank the industry partners, detection services, and SA Water. So they are our long-standing industry partner. Also, I thank Australian Research Council for the financial support. So here's a list of reference for those interested. And here are some photos of the devices we developed and used before. So as mentioned, we've developed all sorts of fancy wave generators. Thank you.
Thank you very much, James. Amazing work. And almost, it's like coming back, joining a full circle again, just like the previous speaker, Ha. So now I would like to ask for questions, invite questions. Those in the audience, if you could please make your way to the microphone here. And those in the watching us online from wherever you are, if you could please submit your questions by scanning the QR code on your screen that is there. And there's a it should be on the screen. So we'll start with questions. If anyone in the audience wants to come up, please.
Thanks very much for your talk, very interesting. My question's to Ha. Many people are vegetarian because they don't want to eat sentient beings. So the key question is, are prawns sentient? Do they suffer?
Are they a sentient being? Do they feel, and are they aware of themselves as being alive? And
do they suffer?
And do they suffer? Yes, not only for prawns, but for fish. That's definitely a question for fish too. And that's something that we're working with as a research organisation as we do research on these animals. And we're working with the ethics committee to improve our practices around these animals and the use of them. But it is really difficult to prove that these animals show or feel pain, as they think, and their biology is so different to mammals. At least for mammals, we can understand and have those links as humans, but for fish and crustaceans, we can't do that. There's been studies done where you prick a fish and then they begin to rub that area. But does that mean that they feel the pain, or they're just irritated from that? The same with prawns. So that's a really, really difficult question. I don't think we can answer it yet. All we can do is try to minimize the stress that the prawns or fish go through. Some might say growth is a really great indicator of their welfare, as if they're stressed or in pain, they won't eat, they won't grow properly, they won't breed. And so if they're portraying all of these normal behaviors, it's a good sign that they're doing okay and in a pleasant environment.
Yes, please. Drew, you are taking the ones online? Okay.
Yes, I am.
Please indicate whenever you are ready, yeah? I'll watch you.
Your leak detection experiments is very interesting. Have you applied that method across different diameters of pipes? Is it applicable? Is the methodology applicable to across all diameters, or would you get reduced results?
Yes, thank you. That's a very good question. From diameter perspective, it's not really a big issue. Well, for larger pipes, of course, you need to generate larger waves, as you can imagine. For smaller pipes, it's easier because you only need smaller waves. That hasn't been really a major challenge. The major challenge actually we experienced is material of the pipeline. So far, we've achieved very good success in metallic pipes, those cast iron, steel pipes. We found it's quite challenging in plastic pipes because, the high signal dissipation and dispersion because, it's a softer material, so the wave can dissipate much faster than in the metallic pipes. So that is one of my, research topic I'm still working on, trying to make the technology more effective in plastic pipes.
Drew.
One here for James. What is the maximum detection distance for your sensors?
Yes, that's another good question. It really depends, depending on what types of waves you generate and what sort of system you're working with. If we use a traditional step wave, as I showed earlier in my presentation, the current technology is relatively large in amplitude, say 5 to 10 meters in pressure. That can propagate kilometers, right? Because in the pipeline, it's really the wave has nowhere to go but just to follow the pipe. So we can actually, one test, cover kilometers. And the travel speed is fairly fast. In metallic pipes, we talk about 1,000 to, let's say, 1,300 meters per second. So within 1 second, so 1,000 meters. So that's why we can cover very, very long distance. That's why this technology is so cost-effective for pipe condition screening. However, we are moving towards smaller waves with higher frequency. So like what I showed at the end of my presentation, those little waves are not going to travel that far, right? As you can imagine, those little waves are fairly small, and due to dissipation dispersion, they can damp out after say 200 meters, 500 meters, depending on the situation. However, the trade-off is we can gain much higher spatial resolution, right? Because we have much more higher frequency components in the wave.
Yes, please.
Thank you to both speakers. Very interesting talks. To Ha, I was wondering if the prawns get any diseases, because it looks like aquaculture is quite intensive. And if so, how are they treated? And then if there's any medications that are used, how's that cleaned up? Thank you.
Yes, thanks for your question. So yes, there are diseases that prawns can get, like any animal. In terms of intensification, the way that prawns are reared can vary from very extensive to very intensive. And the way we manage those systems is how we also need to, how we manage the systems. Disease is a big factor in how that is done. So the more extensive the system is, that means that they're in a natural environment where natural water is flowing into the pond. So that's a vector for disease transmission because the disease is present in the environment before they are introduced into our system. So there are physical structures in place to filter the water, to stop other organisms that are disease vectors going into the prawn system. And so it's a lot harder in those systems to control that disease. Whereas when you go into intensive systems where the water is not being a flow through, it's more recirculated, disease introduction is a less likely of a risk factor, but other things are more of a risk factor, such as controlling that water quality in a recirculating system. You have to get the filtration really right there. And with prawns, we aren't able to vaccinate prawns, so that's not possible. So really it's more about the prevention of disease, and prawns, how they're produced is through cycles. So prawns enter the pond and then they're all taken out of the pond. And so when disease is introduced into that pond, then they all have to be really cold, is usually the main way of controlling disease when disease is present. If it's as bad as creating lots of mortalities, then we isolate that pond and remove all the prawns from that pond.
Thank you.
Thanks.
And so this is a question now for James. So in your presentation, your tests were using pipes surrounded by air. Do berry pipes have issues with passing through different types of ground?
Well, thank you. That's a very technical question. Generally speaking, there's not much influence because the pipe is fairly rigid. Also, the wave we introduced are relatively small. Generally speaking, we don't really want to introduce very large waves. So, the short answer is, well, in air and underground, actually, there's not too much difference for the application. However, there is active research on the topic of fluid structure interaction. So when you have relatively large waves or you have pipes unstrained, relatively loose and can vibrate, then you can have quite significant impact from the surrounding media. Typically, that's not an issue because our pipes, buried underground, properly, are constrained by the soil.
Thank you, James. Drew, do you have another question?
Yes, I do. They're coming thick and fast from our online audience. So now I have a question here for Ha, actually. So in the circular bioeconomy, how much of the prawn's waste leaks out of the farm, and does this hurt any of the neighbouring ecosystems?
Yep, thanks for your question. So Australia's prawn farming is highly regulated, and in the design of the prawn farm, we need areas of water catchment and water treatment. So before the water escapes from the pond itself, which are containing the prawns, it goes through a whole channels of different settlement ponds where the suspended waste settle and are then collected. And the water goes through filtration systems. So, and it can be uptaken again by mangroves in that water catchment area, and algae, which also uptakes all those nutrients. So the water that leaves the pond is never worse than it comes in, but at times it could also be better. And yeah, Australia has a really high standard for the regulations around prawn production.
Thanks, Al. I'll give some chance here. Anyone in the audience? Otherwise, we'll keep going with the online questions. Here's a challenge. Rise up to it. Yes, thank you.
Hi. My question is about leak detection, and I'm wondering, does it work for other things than water? For example, for oil pipelines or chemicals, that sort of thing? Would it have an application, say, in industry or factories?
Yes, thank you. Well, that's another very excellent technical question. The technology should work as long as the fluid is similar to water. That means there's not much compressibility. The problem comes when we have air in the system. So, for example, some of the oil pipes or even gas pipes, even liquid gas pipes. It's not just the liquid, but there are some gas right inside the pipe. Then that will change the the physics fair bit. The compressibility. Once the fluid is highly compressible, the wave can dissipate much faster. So that's the main challenge. But if it's like a fluid very similar to water, it should work.
Thank you.
There's another question from the audience.
My question is for Ha. What about microplastics? How much of them are we actually eating every time we eat a prawn?
Thanks. So that's not exactly my area, but I have been looking a little bit more into microplastics, and there's groups within CSIRO who are working with our Chinese counterparts around this area because it's a really hot topic, especially for the Mekong Delta and that whole region of aquaculture there, where pollution and microplastics is a big concern. Studies have shown that microplastics aren't exactly uptaken into the cells themselves. It's not possible to absorb them. So they're usually flushed out of the system. So any animal would normally not uptake microplastics, so we won't be eating much of that in the animal itself.
That's reassuring somehow. Any other questions from the audience? Drew, do you want to have yeah, can you?
Sure, I'll take them on. So a question here for James now. So can you discuss how the pipe condition assessment improves using your spark generator developed on this history?
Well, yes, in terms of improvement, right?
Yes, please.
Yes, the biggest improvement is in the spatial resolution. So in the past, we stuck with the concept that we had to introduce a side discharge and then shut it off as fast as we can. So we have kept trying different devices to shut off the flow as fast as we can. The biggest difference from that spark generator comparing to the old-fashioned generators is we changed the whole thinking. Right? We don't really introduce any discharge, and we don't think about how we shut it off quickly. We just introduce a cavitation bubble inside the water, and the collapse of the bubble introduce the extremely sharp and powerful pressure waves we need. We can actually control that to some extent, by controlling the voltage we applied to the spark plug, and by controlling the gaps between the spark plug and changing different types of spark plug, we can actually have some control of the cavitation bubble and the pressure wave. And the difference is significant. You can see the duration of the pulse we generated, that's less than 0.2 millisecond. That's pretty much impossible, for any mechanical device trying to shut off the flow, right? So that's the biggest difference, and that enabled us to achieve a very high spatial resolution.
Okay, we'll give the audience here another chance if you would like to ask any questions. While you think about it, I'll hand it over to Drew again. Yes, I can see there are quite a few questions here.
Thank you, Nanda. And so now a question for Ha. So you introduced in your talk about aquaculture being a global industry. Are there many other countries that are adopting the sustainability practices that you spoke about?
Yes. So I should say that specifically for the prawn industry at least, a lot of what is being practiced is already quite circular in that waste have been used to feed prawns since the very beginning of prawn production, really, using things like household waste, prawns also being a predominant species that is aquacultured in like family-sized prawns in more developing countries. So yes, that reuse of resources is quite embedded in the practice of prawn aquaculture. So now it is really refining that process and getting a better understanding of the budget of nutrients coming in and out, and being more efficient at retaining it, and also utilizing industries, waste from industries that complement really well with the aquaculture industry. And yes, so globally, yes, we are not the leaders of prawn research in this space, but we're definitely participating, as well as many of the major prawn producing countries.
Sounds good. I've got a question here for you, James, and I think I dare say this is a question, a burning question from most people that have listened to your talk. Can you give us some insight into the original light bulb or aha moment where the inspiration came from the snapping shrimp? How did that actually come about?
Smart technician, I mentioned that in my slides, and he actually come up with the original idea. He actually helped us with some of the original design of other types of wave generators. Then we reached to a limit that okay, that's the limit of mechanical device, right? It takes time, right, for things to move. As simple as that, right? Physics. Then, one day he came to us and said, look, how about this new but, sounds like crazy but promising idea. Then initially we thought, well, okay, that's interesting, but that's quite dangerous. Right? We talk about thousands of watts in water, in metallic pipes, and, all sorts of questions, right? So how about safety? How about, any damage? Also we know the wave will be extremely powerful, right? As shown in my slide, we talk about, say, tens of meters. So rather than, say, 5 to 10 meters, we generate using that larger device. So there was some hesitation, to start with, but eventually we decided to give it a go and to make a prototype and have a test in the lab, right? The worst scenario is to blow up the pipe in the lab, right? So we did so, and we had some good success. As you can see, the wave was quite large, like tens of meters, but it's really, really short-lived, right? It only lasts for a millisecond less. So that's why the pipe system can still handle that high pressure. And that helps us to achieve the high amplitude or the energy we need and also the sharpness we need. So that's a fairly long story. But as mentioned in my presentation as well, we haven't been able to progress further away, on this because there's lots of hesitation in the industry. When we talk to people about this, fancy spark plug, very good and high voltage, extremely sharp and powerful, they say no. So, but we continued the research. We didn't give up from that point. We recently developed that leak-based condition assessment. That's much more user-friendly, if you like. We just introduce a small side discharge. We don't even bother to shut it off. We just continue the discharge. We rely on the turbulence around that side discharge to provide us the continuous signal. Although it's small, but because it's continuous, we can accumulate the energy. So that's where the advanced signal processing come into play. So we can't just focus on the wave front, the very first wave. We focus on the whole lot of the excitation, so we can have accumulated energy to improve the identifiability. So that's a fairly long story, but that's the short explanation.
Thank you so much, James. I think, although I can see more questions there, but time is coming to an end. So I thank you all for all your great questions from the audience as well as those joining us online. And a big thank you to both Ha and James for joining us tonight and leading us on this journey. This is a surprising journey. And to my co-convener, Drew Evans, who's joining us. We would also like to thank Jira at GR Station Wines and Hauberg Catering for their refreshments that those who could join us here could enjoy. And we thank you all here and online for joining us tonight, and we hope to see you again for the next installment of Surprising Science on the 14th of June this year. Thank you, and a very good night to everyone.